Welcome to the third week of the machine learning module. This week we will discuss various linear and nonlinear regression models. The lecture is split into 4 parts. In the first 2 parts we will discuss multivariate linear regression, including mathematical formulation, fitting, and evaluation. In the third part we will show how penalized linear regression models can prevent overfitting. And in the final part, we will look at nonlinear regression and introduce the kernel trick. So let's start with the mathematical formulation of multivariate linear regression and fitting using normal equation. The application that we will use to demonstrate the regression concepts is neonatal brain growth. Around the time of birth, the brain grows very quickly, and the preterm birth alters the development of the brain. For this reason, preterm brain development is an area of extensive research. We can acquire brain MRI scans of newborn babies to study preterm brain development, and then we can perform segmentations of various brain structures to measure their volumes. So here in these examples, you can see whole brain volume, 6 brain tissues, and 86 brain structures. So machine learning task then is to predict the age of a baby from volumes of the brain structures. And the simplest marker of growth is the whole brain volume. We have seen already this application last week. So in this plot, each circle corresponds to a baby. And on the x-axis, we plot the feature, which in our case is whole brain volume. And we scale this feature using standard scaler. So the volume is scaled, and we have only one feature. Then the target value is the age of the baby, and we plotted it on the y-axis, and you can see that it's in weeks from gestation. And the linear model that we fitted is plotted with a red line here. Here is the equation of the fitted linear model, and we can see that we have 2 parameters. This is the slope, and this is the intercept. We achieved R2 score 0.85, which is quite good, so we can see that the linear model is suitable. But we would still like to improve the prediction. So the question is, can we get higher R2 score, which means we would like it to be close to 1 if possible. So to do that, we have to think, what kind of error do we have in this data set? So it could be 3 types of error, as you already know from last week. It could be bias error, variance error, or noise. So what do you think? Which one is present in this plot? So it is very unlikely bias error because we cannot really see any systematic errors here. The linear model seems to capture the trend in the data pretty well. It is very unlikely variance error because we have chosen a model of low complexity, only 2 parameters, so there is not much space for variance there. So it must be the noise, but unfortunately, noise cannot really be removed by better fit because this is irreducible error in the data. So what we can do is instead is to change the setup. We can include more features. And because you have seen that we have segmentations of 6 brain tissues, we can have 6 different features to predict age at scan, or we can even use 86 different volumes as features. And to increase the number of features, we need multivariate linear regression. So Multivariate linear regression means that we are predicting our target values from multiple features, so more than one features. And you see here we will have D features that correspond to the different brain structures. And our target values correspond to age at scan. Then we have also N samples that go from 1 to N and are denoted by index I, and these samples correspond to individual babies. So here is our multivariate linear prediction model. So we have just one intercept as before, it's W0. And then we have one slope per feature. So we have D slopes to get D plus 1 parameters to fit. And to fit these parameters, we will minimize the loss function, which in this case is sum of squared errors between the expected target values and the predicted target values. So this expression here is just from this equation. So this is how we get the predicted target value y hat. It is useful to express this model in a matrix formulation. So you already know how to construct a feature matrix. So we originally had D columns, which correspond to D features, and N rows, which correspond to N samples. But this time we will have an extra column of ones. And the reason why we do that is because we have one more parameter to fit, the number of features. And that is because we have this intercept here that doesn't have a feature next to it. So we will create a feature x0 like that, that is equal to 1. And that's what we have here in this matrix. And having the feature 1 that models the intercept helps us to simplify the equations. Okay, then next we will have a target vector. And this target vector has n elements that correspond to n samples. And we will also have a weight vector. The weights are our parameters, and we have D plus 1 of these. And then the prediction model can be expressed with a very simple equation. Predicted target vector equals feature matrix times weight vector. And the loss function, sum of square errors, can also be nicely expressed with a matrix formulation. So this is our expected target vector, and this is our predicted target vector, as it's given here by this equation. So this is really the error vector between expected and predicted target values. So we'll do this error vector transpose time the error vector again, which will give us sum of squared errors. So to find the vector w hat, we need to minimize the loss function, and that is expressed by this equation. And to do that, we can set the first derivative of this loss function f with respect to weight vector w to 0. And if we do that, we will arrive in this type of equation. So we have actually an analytical solution for this problem. We can write down an equation for the fitted weight vector w. And this is called a normal equation. This equation is very important because it's the general equation of a least square fit. So note that we have matrix inversion in this equation, but we are inverting a matrix X transpose times X, which is a square matrix of size D plus 1 times D plus 1. So it can be inverted, of course, on a condition that it's not singular, but we will talk about that later. Now, I will show how we can derive this normal equation. So first we'll calculate the derivative of the loss function f with respect to the weight vector w, which is expressed here. And if we do the derivative and rearrange, we arrive in this kind of simple equation. So you see that it's minus x transpose times the error vector. And then we can set this derivative to 0. And if we rearrange this equation, we will arrive at the normal equation. So you already know that linear regression is implemented in scikit-learn in the object linear regression. You've used that already for univariate linear regression. And it implements also multivariate linear regression. There is no difference, it's general. And this object fits the model using the normal equations that we have just seen. So this code is not new for you. You already seen that. So we create the model, linear regression fit the model, and we can print the intercept and the coefficients like this. So here we fit it to the data set with 6 brain tissues. And we see that we have 1 intercept and 6 coefficients that correspond to the 6 slopes. Because we have a simple formulation of the solution through the normal equation, we can also implement it ourselves. So here is how we do that. First, we need to add the column of ones to the feature matrix X. So we will create it using the function mp.ones. And we will add it using function mp.hstack, which means horizontal stack. So you see this is the column, this is the feature matrix. So we have the new feature matrix x1. And then we need to implement the normal equation. So for this we can use NumPy functions. So this is transpose, and mp.matmul performs matrix multiplication. So here we have x1 transpose times x1. So that's this part. Then in this second line, we multiply x1 transpose times y, which is this part. Then we need to invert this matrix, which we do here by mp.linalg.inv. So that gives us the inverse, and we multiply it with x transpose y. And finally, we print the coefficients. And you see we have 7 of them. The first one corresponds to the intercept, and the others are the slope. And if you compare, we have exactly the same solution as previously. So you see that we arrive at the same model. Now is the time to test your knowledge, and you will do that using a quiz on KIDS that is called Multivariate Linear Regression 1. Please do not forget to submit the answers because this is mandatory, and we will monitor your attendance and also how you're doing through this. And after you're done with the quiz, please watch the second part of this lecture that will still focus on multivariate linear regression, but we will talk about fitting using gradient descent and then measuring performance and overfitting.